Hi everyone, I'm Ibrahim Kilinc. I'm a second-year PhD student at University of California, San Diego. Today I'll be presenting our work, which was presented at IEEE BlackSeaCom 2024, titled as Beam Training in mmWave Vehicular Systems, Machine Learning for Decoupling Beam Selection. This is a joint work with Dr. Dreifuerst, Dr. Junghoon Kim, and our advisor, Professor Robert Heath from University of California, San Diego. Before diving into the details of our work, let's get started with the introduction. Let's talk about beam training in mmWave vehicular systems. As you might know, mmWave frequencies provide high bandwidth with data rates for more connectivity for various applications such as vehicular communication, for infotainment purposes, or it might be autonomous driving, and so on. And mmWave frequencies, however, are prone to severe path loss, blockage, reflection, and physical effects due to the physical characteristics of electromagnetic waves at those frequencies. And therefore, directional communication is required for reliable connectivity with high data rates in such systems. The directional communication is enabled by large antenna arrays at the base station and the UE with MIME architectures. And the directional communication is achieved by beamforming that is mostly done using codebook-based approaches in industry standard arrays. And the receive and transmit beam pairs from these large codebooks needs to be configured to enable directional communication. The configuration is, however, tied to a certain time duration, which is called beam coherence time. And the beam coherence time is the duration of which a transmit and receive beam pair is valid for reliable communication. And the beam pairs needs to be configured or readjusted within such time intervals. And as you consider the coherence time, some portion of this time needs to be allocated to beam training, which is the configuration of transmit and receive beam pairs. And let's consider a fixed antenna configuration at the UE and at the base station, and fixed codebooks, and determine subset of beam pairs from all codebooks of the base station and at the UE. And the beam sweeping is the only overhead of training for fixed antenna configuration, and the same codebooks for all UEs with determined beam pairs to try. And as mobility increases, coherence time decreases, and as the antenna elements increases, narrower beams leads to larger codebooks naturally, and in turn, training time increases due to search space increase. When combined antenna element size, codebook size, mobility, there is an optimal configuration that maximizes the data rate. And therefore, efficient beam training for maximizing system performance is required in mobile vehicular systems. The beam training problem was tackled by many approaches in the literature, and one of the solutions to that problem is to use side information in the form of which might be in the form of radar, LiDAR point cloud, location, or camera images, which were taken by UEs or base stations. And using the side information for the beam selection is to decrease overhead of beam sweeping, and it was proposed in the mentioned works. And there are some other work focusing on codebook design utilizing side information. In this work, we will be focusing on beam selection. And the common approach in the literature is to have a centralized beam selection engine that selects the subset of all beam pairs based on the side information. And I will refer to such selection as coupled selection from now on. And side information, as you might know, is mostly produced at the UE side, thanks to the sensors that the UEs are equipped with, such as radar, camera, or localization sensors. And in such centralized beam selection methodology, the side information transfer is required to the centralized engine if the side information is not in the centralized entity. And this is one of the challenges of the coupled beam selection. And the overhead is in real time, which occupies time duration from the beam coherence time, and accordingly decreases time for data transmission. And the second challenge arises when the UEs have different antenna structures or even different codebooks. And the beam selection method needs to account for the antenna specifics in real time so that the beams can be selected for different codebooks or different antenna structures. And also the beam pair information needs to be shared with the other entity from the centralized engine. And the third challenge comes into play when the side information from the user to the centralized engine is not transferable due to either privacy constraints or UE preferences. Then the UE and the base station has to exhaustively search all the beam pairs or fall back to another strategy, such as hierarchical search. And when the base station doesn't have this information, the side information can be still used by the UE side. And the research question is, what is the way to deal with these challenges? And our main idea in this work is to decouple the beam selection between the base station and the user using the location information. We are focusing on the location information in this work, since it's one of the simplest sensory information to obtain, process, and share, compared to the other informations that I mentioned. And in the decoupled beam selection, the UE selects its beam based on its location information, regardless of the base station beams. And likewise, the base station selects its beams independent of the UE beams which were selected, depending on the available information at the base station. And in the beam sweeping stage, the Cartesian product of selected base station beamformers and the UE combiners are swept through to find the beam pair, providing the best performance matrix. And what are the advantages of the decoupling? There is no need of the UE location transfer if the UE doesn't want to share the location information at the base station. And the UE can still utilize the location information without sharing it with the base station. And there is also no need of sharing beam pair information, because each entity, the base station and the user, selects its beams independent of each other. And the configuration specificity can be embedded into beam selection engine because of the decoupled methodology. And the UE can also predict its beam over trajectory in an offline fashion, where the UE knows its speed and the acceleration over the trajectory. And UE can still leverage its location even though the base station has no access to it. And the key question is, the decoupling seems to have some advantages over joint beam selection, but is decoupling beam selection performance worthwhile? Let's have a look at the system model that we are considering. In the wireless system that we are considering, the base station is equipped with uniform planar array and does analog beamforming through phase shifters. And similarly, the UE is equipped with uniform planar arrays and does analog combining through phase shifters. And you consider OFDM system, and calligraphy W denotes the UE codebook, and calligraphy F denotes the base station beamformer codebook. And H denotes the channel matrix at gate subcarrier. And we calculate the average rate over subcarriers as follows. And we define a notion called throughput ratio for given channel realization and selected beam pair subset calligraphy S, where calligraphy B denotes set of all beam pairs as given. And throughput ratio is the maximum rate achievable by the subset divided by the maximum rate achievable over all beam pairs, which we use to define the beam selection problem. We define the general beam training problem as follows. Let's consider a region of interest in the urban street, where the UEs might be located in any place in the region of interest. And the beam selection problem is to construct a beam pair subset S for any location in the urban street and region of interest to maximize the throughput ratio subject to the cardinality of selected beam subset equals to NB. And this maximization translates to the question how this S is constructed in a coupled or decoupled fashion with what information. To answer this question, we consider three scenarios, where the first scenario is our baseline case. The beam subset S constructed with coupled beam selection with location information as in the literature. The second scenario is to select subset S in a decoupled fashion with location information. And the The analysis between first and second scenario is to quantify the performance gap between coupled beam selection and decoupled beam selection. And in the third scenario, we consider decoupled beam selection without location information at the base station. And the comparison between first and second scenario leads to the evaluation of the performance gap due to the disaggregating location information from the base station. And the general beam training procedure is first to train beam selection method to configure its parameters for the beam selection. And in the second stage, the information is fed into the model and set of beam pairs is predicted. And then beam sweeping is done over the constructed set and beam determination is done to determine best beam pair. Let's look at the beam training scenarios more closely. In the first scenario, the base station has a model that predicts the beam pair subset S based on the location information. And the UE is assumed to have its location through localization sensors. And the UE location is transferred to the base station. And the beam selection approach is joint beam selection. And in the second scenario, the base station and the UE has a separate model where the base station model selects a beamformer subset from the base station codebook, and the UE model selects based on the UE location a subset of UE combiners, such that the throughput ratio is maximized. Again, the available information is the same, and the beam selection approach is decoupled beam selection. And in the third scenario, the only difference from the second is the base station doesn't have the location information. And the base station model predicts a subset of beam pairs from the base station beams so that the subset covers the entire region of interest to maximize the throughput ratio. Let's look at the beam selection method for different scenarios. In this work, we configure the beam selection models using a dataset illustrated in the brownish table. And we assume the same dataset is used for all scenarios for fairness. We do not specify how these models are trained and dataset is collected in real implementation. And it's one of the future extensions of this study. And let's look at the table. The table consists of throughput ratio measurements for all beam pairs in the calligraphy B for specific locations. Such dataset can be collected through derived tests, even with some people permitting to share location information in a short amount of time. And each row of the table is called as throughput ratio vector for a specific location. And there is another expression that we denote as approximate throughput ratio for the base station beamformers and the UE combiners. And for the J base station beam, the approximate throughput ratio is calculated by the mean of the throughput ratios for the J base station beam over all UE combiners. And the approximate throughput ratio for UE combiner is calculated using the same methodology. And this procedure can be thought of calculating the marginal throughput ratios provided by the base station beamformers and the UE combiners. And in the first scenario, for the beam selection method, we consider a regression model which predicts the throughput ratios given the location information for all beam pairs. And then after the prediction, NB beams with the greatest throughput ratios are selected for the first scenario to construct beam subset pair S. And in the second scenario, the base station has a decoupled regression model and the UE has another model for itself. And given the location information, the approximate throughput ratios for the base station and for the UE is predicted using their own models. And the base station beams and the UE beams are selected based on the greatest approximate throughput ratios. And in the third scenario, the base station doesn't have the location information of the UE to predict the subset of the beams. And we assume that the beams in closer locations are similar to each other because the multipath characteristics of similar regions are similar to each other. And the base station has the location-based data set that we mentioned, and we use a clustering idea to cluster the data set over the locations and then make a probabilistic beam selection for the all clusters so that the selected subset can be served can serve the entire region of interest. You can check out our paper for further details. And let's look at the simulation results of our work. The vehicular simulation scenario that we consider in this work is an urban street in Paris. In 4-lane roadway, there is a base station next to the roadside, which is mounted on a building wall. And the buses are reflectors and blockers in the scene, and the UEs are the cars with antennas on top of their roof. And simulation parameters are given as follows. And the channels were generated based on these simulation parameters in Siona, which creates spatially consistent ray trace channels. And the performance matrix that we consider is throughput ratio, which is the average throughput ratio over all test cases. And the misalignment probability is the probability of not including the best beam pair in the selected subset S over the test cases. And for the regression task, for throughput ratio and approximate throughput ratio, all for different scenarios, we evaluated live-weight neural networks, random forest, XGBoost, and linear regression, and the XGBoost outperformed all the other three. Then we used XGBoost in our simulation results. We specifically consider live-weight models because these models will be deployed in the UEs, which needs to be memory efficient and should have a less inference time. In this slide, we present the performance gap due to disaggregating location information at the base station. And the heat map shows the throughput ratios for varying number of base station beams and varying number of UE beams, which are selected for the second scenario on the left and for the third scenario on the right. And the key takeaways from these two heat maps are: disaggregating location information from the base station leads to a sharp throughput ratio decrease, up to 20% throughput ratio loss in selecting very few base station beams. And the clustering idea recovers the performance loss when more than approximately 10 beams at the base station are selected. And note that the selecting 5 beams at the UE is enough to achieve about 90% throughput ratio. In this slide, we compare the performances of all three scenarios. And for the varying number of beam pairs in the x-axis is due to the increasing number of selected base station beams, where the UE beams, the number of selected UE beams is set to 5, which we highlighted in the previous slide. And as you can see, the yellow curve is the baseline, and the red curve is the second scenario due to the decoupling beam selection. And the third one is decoupled and disaggregating location information from the base station. And the key takeaways from this throughput ratio plot is decoupling with location or without provides a comparable throughput ratio to coupled with location when approximately 10%, which is around 100 beam pairs, are swapped. And in terms of misalignment probability is a metric that is harder to achieve. And decoupling beam selection and disaggregating location information leads to more misalignment while achieving a decent throughput ratio comparable to the first scenario and second scenario in selecting approximately 10% of total beam pairs. The first key takeaway of our work is decoupling the beam selection with the presence of UE location performs very similar to the coupled beam selection, which shows that decoupling does not deteriorate the performance of the beam selection as compared to the joint beam selection. Therefore, the beam selection methods specific to UE can be developed to exploit the sensor information that is already available at the UE side. And disaggregating location information from the base station leads to a performance decrease, but clustering UEs into small regions helps to recover the performance. Even though base station doesn't have the sensor information, it can still utilize some old data which can increase the performance of the beam selection and accordingly the data rate. And in this work, we assume that the dataset exists and the UEs are deployed with the models. And in our future work, we are planning to analyze the practical aspects of decoupled beam training and how to exploit decoupling for heterogeneous devices. Thanks for taking time and watching this presentation. If you have any questions, you can reach out to me, or you can check out our paper for more details, which is in our IEEE Explore.